So today, we're talking about vectors and planes. You guys are going to be able to apply properties of vectors to planes instead of lines this time, okay? So the focus is on planes. We talked about lines last class, and then we'll have applications, and then that will wrap up vectors. So the vector equation of a plane is vector R is equal to vector A, which is essentially your position vector, okay, of a known point that's on the plane, okay, similar to what it was for lines, plus S times vector V plus T times vector W. Okay, so S and T serve as scalars, just like what lambda did when we were talking about the vector equation of a line. But here we have two parameters, and we also have two vectors, W and V, which represent any two non-parallel vectors that are parallel to the plane. And if you recall, a plane from geometry is a three-dimensional figure, extends indefinitely in all directions, okay? Well, if you have a vector that is parallel to a plane, that basically means that it's traveling along the vector, it's essentially you are traveling along the vector and staying on the plane at the same time. So, I know we're talking about something in three-dimensional space, but remember this is what a plane looked like if you were to draw it. So, essentially, this right here would represent two non-parallel vectors, okay? They're parallel to the plane because they essentially run along the plane in the same space. Mm-hmm. Does that make sense?
Pencil on a desk.
Yeah, like a pencil on a desk, but if like the pencil was like within the desk, essentially. Yes. Okay? But that's the equation that you need, okay? So kind of very similar to it for a line, but you have essentially two non-parallel vectors with two different parameters.
Are they parallel to the plane or are they on the plane?
They're technically, they run along with the plane, but they're considered parallel to the plane. Okay, so like you said, like a pencil on a desk, but just pretend like that pencil's like fleshed into the desk. So it's technically still parallel to the plane. Okay?
In the plane.
Yeah, in the plane. Now, a vector is normal to a plane if it's perpendicular to all vectors that are parallel to the plane. And you have this image here that's already drawn for you, okay, to represent that. So in this diagram, you see N is a vector that's normal to the plane. It's perpendicular to the vectors that are parallel to the plane, aka on the plane. Okay? When you have a vector that's normal to a plane, there is an alternate way that you can write the vector equation, and it's how you would want to write the vector equation when you're given a normal vector, and that's on the next slide. So we would do the dot product between some vector R, that normal vector that's perpendicular to the plane, and then another vector that's on the plane. So remember, R and A represent the vectors in which the normal is parallel to, and then N is your normal vector. So essentially, this is how you could create a vector equation of a plane. And you'll see how this is used in some future examples. Yes, good? If a plane has a normal vector N, A, B, C, of course those, components, and passes through a point, X, Y, Z, then the Cartesian equation of a plane is given to you here. AX plus BY plus CZ, which essentially is equivalent to each one of these components times each one of these points equal to D, where D is a constant. Okay? So each component in the vector, the normal vector, multiplied by each of its respective points. Remember, the top goes with X, middle one goes with Y, last one goes with Z, and it will equal D, your constant. So essentially, these are all your formulas that you need to write your equations of vectors in the plane. We're going to look at some examples next. So let's take a look at some examples of writing different equations, finding points, et cetera, that essentially are working with vectors in a plane. Okay? So here's the first question. It says to find the equation of the plane with a normal vector of 1, 2, 3, and which passes through the point -1, 2, and 4. Okay? This one's like your very easiest question. Okay? Reason why is because remember you have the equation AX plus BY plus CZ is equal to D. Okay? Oh crap. Was I not recording? Sorry, I don't think I was recording on this one. So I'm gonna go back real quick and explain it. Okay, I'm recording now. So we take the equation of our vector. Okay, we plug in the values of 1, 2, and 3 for C. That's what we did here. Okay, and then we take the coordinate -1, 2, and 4 and plug it in for capital X, capital Y, and capital Z. The actual product of that and the sum will give us the value of our constant D, which is 15. And then the front half, when you equate to 15, is the equation of our plane. Here's an example of where we're not given the actual vector, the actual normal vector, and so we're going to have to essentially do a few things, a few properties of vectors in order for us to get the pieces that we need to create our equation. Okay? And since we're writing in two different forms, remember the vector form is the one from the very first slide. That was vector R equals vector A plus S times vector V plus T times vector W. And remember that vector V and vector W were two non-parallel vectors. So essentially what you need here is two non-parallel vectors. Okay? Those vectors are created from those 3 points. Okay? But remember, when we're doing this, does everybody have the question written down? Okay. I'm gonna go back to the diagram. Okay? So essentially we need this and this to create this vector equation. Okay? So they should have a shared point, of course. We only have 3 anyways to work with. So we can use vector AB, and we can also use vector BC. We can even use AC and BC. We can even use, no, those are our only 2 options here. We need two non-parallel vectors, and so we must have a shared point. So we either share B, we could share C, or we could share A. Okay?
How do you compare the vectors again?
It can be any combination, but they have to have a shared point because we're trying to create the 2 non-parallel vectors, which means they have to have one like I mean, I don't know how else you could do it, but A, B, and BC is one of them. You could have done AC and CB. You could do BA and AC, okay? And so it's not going to, of course your answer may be a little bit different, but it's not going to fully mess up anything. They just have to be two non-parallel vectors. How do I find vector AB? This is old.
Subtract A from B.
Subtract A from B, so that's going to be 3 minus a negative 1, 1 minus 2, and 1 minus 0, which is
4, negative 1, 1.
okay. And then we're going to do the same thing to find BC. So that's going to be 1 minus 3, 0 minus 1, and 3 minus 1, which is
Negative 3, negative 2, negative 1.
Negative 3.
I said negative 2.
Okay.
I corrected myself. And negative 1 and 2.
there we go. So then this is essentially represents our V vector, our W vector. So for our two non-parallel vectors, now all we need is a point, a fixed point, okay? It does not matter which point that you use, okay? But, I mean, it doesn't hurt just to use the first one. So we're gonna have R, vector R equals vector A, which is gonna be our fixed point, which is negative 1, 2, 0, plus S times vector B, so that's gonna be plus a parameter, 4, negative 1, 1. Then we need a second parameter and another non-parallel vector, which would be W, so plus T times negative 2, negative 1, positive 2. And that's how we do the vector form for the equation of a plane.
We don't have to find S or T.
No, not just to write it. Well, you have to in the future. It's a possibility, but I didn't run into any examples that had that.
Could you find the normal vector and do the other vector equation?
The Cartesian?
No, the R dot product n equals A dot product n.
Mm-hmm, yes. Alright. So now let's do it in our Cartesian form. Remember our Cartesian form is the AX plus BY plus C equals, the rest, okay? This is where we would need to find that normal vector, okay? We would need to find that normal vector that's perpendicular to our two non-parallel vectors that are on the plane. So in order to find n, we would need to do what?
Cross product of V and W.
We would need to do the cross product of V and W, okay? Because, remember, perpendicular, that involves the cross product, and we're going amongst these here. We also talked about that. I can't remember which lesson it was. I think it was 3. I think it was actually our last lesson. I think it was our last lesson. So in order to find n, we need to do the cross product between B and W. So we're going to do the cross product between these two. Remember, that's when you do A2 times B3 minus A3 times B2 and so on and so forth. Okay, can you guys find the cross product? So once you do that, remember that's equivalent to n. Okay, that's your normal vector. And remember, we're writing in Cartesian form. That is what goes in for our, the ABC. Okay, so then we just need a point to represent the capital X, the capital Y, the capital Z. And that's going to help us find our constant. Which one are we going to use? Huh?
Does it matter?
No. So you want to use A again? All right. So then we'll have AX plus BY plus CZ. I'm just writing this out more so for the video's sake. So then A is -1, so that's going to be a negative X. B is a -10. C is a -6. So then we plug in the point A for the capital X, Y, Z. So a -1 times a -1 plus a -10 times a +2 plus a -6 times 0. That's going to be equivalent to -19. And so we'll have -x minus 10y minus 6z, which is equal to a -19, or x plus 10y plus 6z is equal to a +19. Either one would be acceptable. And so that's how we can write vector equations of a plane when we're not given the actual vectors. We actually have to find them ourselves. Another example. We're going to find the parametric equation. So we'll hit all three different equation forms that we've talked about of a line that goes through A and B, and then we're going to figure out where this line actually intersects with the plane that has that respective equation. So this time we're not finding the equation of the plane, we're actually finding that point where we're actually trying to figure out this point here where a line would intersect that plane. Okay, so that's what we're actually finding here. So we have A and B, the 2 points that make up the line. We're going to find the equation for that, and then we're going to find the point where it intersects with the plane that has that respective equation. Do we remember that parametric form is the one where it's like x equals, can't remember the exact form. I don't know if they use A, B's, and C's from before. But essentially it's the vector equation that's essentially split up into the x, y, and the z. Okay? How would I go about finding lambda? Because this is the equation of a line, so it's incorporating what we did last class to this class. Was it A, B, and C?
X equals A1 plus lambda B1.
Mm-hmm. Ah, yes, okay. So this is what we talked about when we did equations of lines with vectors. And so in order to write the parametric equation, I essentially need to know what the B vector is, and then A is just going to represent one of the fixed points. How did I find vector B? Remember, this was known as the direction vector.
So B minus A.
So that's going to be B minus A. So this is incorporating concepts from our last lesson when we did lines. To find our direction vector, we would do B minus A because we actually need that vector. So when I do B minus A, what do I get? okay? And then I need to use a point for the A1, A2, and A3. You just want to use point A. So my parametric equations are going to be -1 plus lambda, plus 3 lambda. Y equals 2 minus 2 lambda. And then Z is going to equal 3 minus 6 lambda. So that's the first part of the question. Those are our parametric equations. Remember, hence means I need to use what I just found. So in that way I can figure out that point where they actually meet with that plane. Okay? So if this equation, x minus 2y plus 3z equals 26, is the equation for the plane, I'm trying to see specifically where this line that has this particular equation here meets, which means I'm going to plug in each of these values for the x, y, and z into the equation. So remember, if you want to figure out where they intersect, you would technically set them equal to each other, but here, since these are already solved, we would just plug in.
Oh, and then plug that value into the equation of the line.
Exactly. And then once I figure out the value of lambda, I'm able to actually figure out the point where the line would intersect with the plane, because it would be the shared point between both things. So I'm going to plug in -1 plus 3 lambda minus 2 times 2 minus 2 lambda plus 3 times 3 minus 6 lambda equals 26. Again, I'm plugging that in because I'm trying to figure out what the value of lambda is by using both pieces, the line and the vector, the line and the plane. And then I'll be able to plug in the value of lambda to actually get the point where they intersect. So simplify. I'm just distributing, combining like terms. It's -11 lambda
22.
equals 22.
That's what I got.
Yep, because you got 4, so then subtract 4 from both sides, 22. So lambda is equal to -2. So then to find that point where they meet, I'm going to plug lambda back into my parametric equation to get the point -7, 6, 15. And that is where the line and the plane meet for that particular equation and the line that goes through those points. Okay, so suppose n is at the foot of the normal from A to the plane that's given to you. Find the coordinates of n and hence find the shortest distance from A to the plane. Okay, so essentially you have a plane and you have a line that is normal, aka perpendicular to the plane. N is at the foot of the plane, and so this is the coordinates that you're looking for. A is some point that lies on that line, and then you have the equation of the plane. Okay, now in order to find n, you need the normal vector. What's going to be the normal vector?
One minus 1 plus 2.
And how'd you get that?
From the formula, it'd be the A, B, and C of the plane equation.
Exactly, it would be the A, the B, and the C of the plane equation. Okay, so now that I have my normal vector, okay, this is also technically the B, because that's the direction for the line. Okay, so this is also indirectly the direction vector for the line. And so I can create my parametric equations using A as my fixed point and my direction vector, which is my normal vector, remember, because it's perpendicular. So I can create my parametric equations, x, y, and z, as 2 plus lambda, -1 minus lambda, and then 3 plus 2 lambda. Again, I can use this because that normal vector tells me the direction in which this line is coming down to the plane, perpendicularly. Okay? And now that I have my parametric equations, remember I'm trying to figure out that point where the line intersects with the plane. I'm going to take each one of these equations, plug it into my equation of the plane to find lambda, to plug in to find n. Okay? So, 2 plus lambda minus a -1 minus lambda. Be careful because since it's a minus y, we want to make sure we subtract all of y. Plus 2 times 3 plus 2 lambda is equal to 27. Again, we need to find the coordinates of n, and we do that by taking the parametric equations and plugging them into the equation of the plane to find lambda. Can you go ahead and find lambda? Anyone? 3. So if lambda is equal to 3, then n is going to be 2 plus 3, -1 minus 3, and then 3 plus 2 times 3. Those are the coordinates of n. Remember, because this equation can give us any point that's along that vector, but specifically the one that is on the plane that's perpendicular is that point. How do I find the shortest distance from A to the plane?
Magnitude of n.
I need to do the magnitude of, you mean the normal vector n?
Can you see the distance variable between A and N?
You would do essentially the distance one between A and N, or the magnitude of vector A n. You want to do the magnitude
Is
of,
it the same?
it's the same thing,
Yeah.
okay? Because again, to find the distance between 2 points, because remember n is actually on the plane, we can either do old school distance formula with 3 coordinates, or you can find vector A n and then just do the magnitude of that, which essentially is the same thing, okay? So A n would be 3, -3, no, that's not right. 5 minus 2 is -4 minus a -1 is a -3. 9 minus 3 is 6. Nine and 36. What's 9 plus 9 plus 36?
9 plus 9 plus 36. I think it's 54.
54. Yeah, 36 plus 18, yeah, 54. So that simplifies down to be what? The square root of 54.
It can't be simplified down to 3 root
3 root 6.
6. Oh.
So then that would be the distance, the shortest distance. Remember the shortest distance between a point and a plane or a point and a line is that perpendicular distance. That's why we did figure out what the value of n was first. That's few formulas. To find the angle between a line and a plane, it is sine phi is equal to the absolute value of the dot product of the two divided by the magnitude of the two. And we're going to do this example here. We're going to find the angle between a plane and the line. N and D essentially represents the direction vector for the line, and then that's what D is, the direction vector for the line, and N is the same N, the A, B, and C for the plane. Okay. So the N goes with the plane, the D goes with the line, specifically the direction vector of the line. So what's N?
X plus, oh wait, no.
1, 2, -1.
1, 2, -1.
1, 2, -1. And what's D?
One, -1, 2.
1, -1, 2. Because remember, a parametric equation is set up. And remember, B is that direction vector piece for the X, the Y, and the Z. So that's 1, because that's what's attached to the T, -1, and then +2. So we need to do the dot product and take the absolute value of N and D if necessary. So old school dot product. That's going to be 1 times 1 plus 2 times -1 plus -1 times 2. We're going to take the absolute value of that. If necessary, it might be a positive number. We're going to divide that by the magnitude of N. So that's 1 squared plus 2 squared plus -1 squared. And we're going to multiply that by the magnitude of D. 1 squared plus a -1 squared plus 2 squared.
Really the same thing.
So I have 1 plus a -2 plus a -2. What's that?
-3.
And so I'm going to take the absolute value of -3, which gives me a
3.
+3. 1 squared plus 2 squared plus -1 squared. What's that? √6. And yes, these two are the same thing. It won't always be like that. It just happens to be this time. So that's another √6. What's √6 times √6? 6. What's 3/6?
1/2.
And to solve for an angle, you always have to do the inverse. What's the sine inverse of 1/2?
3.
Because on the unit circle, sine is the what coordinate?
Bottom.
Is sine x or y?
One.
It's y. So we're looking for the y coord where y is 1/2, and that does occur at 30 degrees, or pi over that's the angles. Well, pi over what? What's 30 degrees? Pi over what?
6.
There we go. Can't predict.
I'm a bit rusty in unit circle.
Alright. It's not that bad. The angle between two planes is found by using vectors n1 and n2, and theta is the acute angle that's in between them. So what you see on the left is like the three-dimensional aspect of it. What you see on the right is the viewpoint, like that view here point, and essentially what it is that you are using. Okay? So N1 and N2 are on your two different planes. The acute angle that lies in between them can be seen in plane 2. If you want, I can take screenshots of these and put them on Schoology if you don't want to try to recreate them and draw them. But to find the acute angle between two planes, don't get twisted. This one is cosine, sorry. Don't get it twisted. Like I just said it incorrectly. It's cosine between two planes. It's sine between a line and a plane. But it's essentially the same formula. The absolute value of the dot product between the two planes divided by the magnitude of it. So we're going to look at an example there, and then that's going to be it for the day. There is a little bit more that goes with this concept, but we haven't learned row reduction, and so I'll have to come back and revisit it once we go over row reduction. But it's basically how to like deal with like three planes, and how to like find the point where three planes intersect, or the line where three planes intersect, where two planes and one plane intersect, and so on and so forth. Several different things. But we need row reduction for that. All right, so we're gonna find the angle between the two planes that have those respective equations. X plus y minus z equals 8, and 2x minus y plus 3z is equal to -1. Remember, you need n1 and n2 from both vectors. Remember, that's the a, b, and c. So that's 1, 1, and -1. And then that's 2, -1, 3. And you would plug it into the formula to find the angle between the two planes. So then we do the dot product between the two. Remember, this is sine phi. So I'm going to do the dot product. 1 times 2. Plus 1 times -1, plus -1 times 3. I do the absolute value of that. Remember, that's at the top. Now I'm going to divide it by the magnitude of both vectors. So that's going to be sine phi equals, oh, it's not sine, my mistake. I am entirely wrong, because this is between two planes, not a plane and a line. Sorry, the transition out of class and the hecticness threw me off, so I do apologize. So the numerator is going to be 2 minus 1 minus 3. So that's going to be a -2, but it's going to turn into a +2 because it's absolute value. This is going to be over the square root of 3 times the square root of 9 plus 1 plus 4, that's 14. So that's 2 over the square root of 42. I'm going to do the cosine inverse because I'm looking for the angle. And so the angle between these two planes, the acute angle, is 72 degrees. 72.0 degrees, because I rounded 3 significant figures. Okay? So that's how we deal with vectors in a plane. That's how we find angle between different planes. We do have intersecting planes and how to find the line that intersects them, because remember, two planes intersect the line. So if you have three planes. They're going to intersect at a line as well, or maybe different lines. But we have to learn row reduction operations in order to be able to do that. But essentially, this is what we're going to be dealing with once we do row reduction operations. That's going to be separate from vectors. So we're going to deal with two planes in space, intersecting, parallel, coincident, and then also with three planes, okay? So again, we will revisit this after we learn row reduction operations, but in the meantime, just make sure you know how to find the equation of a plane using vectors, and how to find angles between vectors, the angle between planes, as well as a line and a plane.